How's everyone? Having a good weekend? Okay. All right, I have nothing. This is all on you. So, yes.
On the practice, can you explain that range of T problem to find the range of LT
Of the trace. Okay.
trace?
So, is everyone okay with me working practice midterm problems? Has anyone saved it? I don't want to spoil the exercise. Okay, so one of the it was on the practice. So one of the practice midterm problems sets up this linear transformation T, which goes from the set of 2 by 2 matrices, which we're denoting M sub 2 by 2, to R. And the way it works is that if you want to apply T to some matrix, you add the diagonal entries. Okay, so that's a real number. A matrix originally has real entries. We've picked out 2 of them and added them, so that's a real number. That's why the codomain of this linear transformation T is R. And this transformation has a name. It's called the trace. But whatever, it's not so important here. The question is, what are the rank of T and the nullity of T? So what are some thoughts? There's tons of seats. You guys can come on in. What should we be thinking about if we want to figure out the rank of T and the nullity of T? Yes?
Per rank, where the transformation is bound.
Yeah, we want to know the range of T, because if we know the range of T, that'll tell us the dimension of the range of T, and that's the rank. So what is the range of T here? Just think of it as a function. What's the set of real numbers that you can get out as a sum of 2 real numbers situated on the diagonal of some 2 by 2 matrix?
Numbers.
Yeah, all real numbers. So the range of T, the image of the domain under the function, is equal to the whole real line. Because, for example, what kind of matrix could I use to get me some particular value x out? What would be a matrix? Give me 4 numbers where if you add those 2 diagonal ones, you get x. Yep. Yeah, that's fine. Right? So definitely, no matter what real number x you're thinking of, I can give you a matrix that has a trace which is equal to x. So now that we know that the range of T is the whole real number line, what is the rank of T? 1. That's right. Okay, if that feels uncomfortable, you can write R as R to the 1. Right? Rn is definitely n-dimensional, so R1 is 1-dimensional. If you prefer to think more fundamentally, notice that just the number 1 is a basis of R1, because you can realize any real number as some constant times 1. All right, whatever. That's the rank. What about the nullity? How can we figure out the nullity of T? Yes.
When A equals negative D.
Yeah. What you want to be thinking about here is what does it take for T to map something to 0? What sort of thing gets mapped to 0? If we can understand the space of vectors, or in this case matrices, that get mapped to 0, then that's going to tell us what the null space is. Then we just figure out its dimension. That's the nullity. So the null space of T is the set of matrices such that the two diagonal entries are negatives of each other. Right, just all the matrices where the bottom right is equal to -1 times the top left. Those are going to get mapped to 0 because when you go to add the diagonal entries, you get 0. Does that make sense? And then what's a basis of this? Let's come up with a basis for this space, because then we can just count how many vectors are in it. That'll tell us the nullity. So what should we be thinking here? If we want to come up with a basis for the set of all 2x2 matrices whose diagonal entries are opposites, additive opposites of one another, what can we do? Yes?
You got one matrix with 1, 0, 0, -1.
Great. You can have one matrix that's 1, 0, 0, -1. Okay, that'll give us the sort of diagonal piece. But the span of the list containing only that one matrix will never give you non-zero stuff on the off-diagonal, whereas in reality we can have whatever we want in those two off-diagonal spots. So what are some more matrices we should throw in there? That would work, but I'm going to make it a little easier than that. And just give myself a control just in that top right since it's not constrained. But yeah, you could do 0, 1, 1, 0. That would be fine. Just make this last step a little trickier. And then what's my last basis vector going to be here? Yes?
0, 0, 1, 0.
Yeah, we should give ourselves a 1 in that lower left position too. So now it's clear we can get any matrix of this form as a sum of these three matrices times each one times some weight. And if that felt a little fast, I'll fill in an extra step here, which is hopefully very familiar to you. I'll split this up and write it as A times 1, 0, 0, -1 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0, where A, B, and C are just any real numbers. And by definition, that's the same thing as the span of those three matrices. Yes? You mean just replace the pair of them with their sum?
Yeah.
You could, but it wouldn't span the null space because there's no constraint on B and C. So B could be 7 and C could be -11. That would be fine. Whereas any linear combination of just those two matrices, the first one there and then the sum of the second and third one, would have to have B and C being equal. So you wouldn't be able to reach some of the matrices that you want to be able to reach. All the ones with A equal to minus D, but B not equal to C. You wouldn't be able to grab them. All right, and then this list is definitely linearly independent because if you have some linear combination of those four matrices equaling the zero matrix, then definitely all the weights have to be zero because they have no, all of their non-zero entries are in different places. Right. Another way to say it is if A, B, C minus A is equal to the zero matrix, that forces all of A, B, and C to be zero. Okay, so anyway, this is definitely a basis now. We see that it spans our null space and the vectors are linearly independent. So what does that mean the nullity is? Answering and raising your hand at the same time. That's right, it's 3. We have 3 vectors there. All right. Yes.
How does the rankless nullity theorem come into play for this particular?
Yeah, so we could have skipped this second part of the calculation if we could have decided on the dimension of the domain. Because we know from the rank nullity theorem that the rank plus the nullity equals the dimension of the domain. And what is the dimension of the set of 2 by 2 matrices? 4. Yeah, you have 4 free choices to make, 1 for each entry. Oops. So that's a list of 4 matrices. Just give yourself a 1 in each position. And that's definitely linearly independent for the same reasons as before. And it clearly spans the set of 2 by 2 matrices because whatever 2 by 2 matrix you have, you can achieve it as a linear combination of these ones by just putting the 4 entries as the 4 weights. So, so the dimension of the set of 2 by 2 matrices is 4. And that means that the rank nullity theorem works. Yes?
What's the difference between that span and the idea that these matrices can't span greater than R2 because there's only 2
The matrices here are the vectors in our vector space. So they actually, their role as a linear transformation is not present in this problem. You should really think of, if someone is treating the set of matrices of some dimensions as a vector space, you should think of it more like R4, where they just decided to write the bottom 2 entries over to the side instead of underneath. Right? You shouldn't think of it that way if the matrices are acting as linear transformations. But here they're not. They're the static objects that are being studied by virtue of this other transformation that's taking their trace. They're not themselves playing the role of any sort of transformation. Yes?
Just to be clear vocab-wise, the null space refers to the span of the appropriate basis, whereas the nullity refers to the dimension of that basis.
The null space refers to the whole vector space of vectors that map to 0 under the linear transformation.
Right.
The nullity just refers to the dimension of that space. Right. You guys can filter in.
Thought about it. So many people have their desks up already.
All right. Yeah.
Do we need to memorize the 10 axioms?
You do not need to know the 10 axioms. No. I don't memorize them, so I shouldn't ask you to. Actually, I don't think I know anyone who could list them off the top of their head, except people who have some immediate reason to do so related to a class like this one. Yes.
So it's
Yeah, there seems to be a great deal of confusion about C01 in general, and that's my fault because I didn't spend a lot of time on it, reasoning that it was all very familiar to you, most of you having taken a calculus class recently. So these two graphs I've drawn here are graphs of functions in C01. This is, in my opinion, how you should think about what vectors in C01 look like. Okay, so a vector in like R2 or R3 is just an arrow that points from the origin to some point, or if you want, you can just think of it as that point. Here, you can't think of a vector as just a point because it's got a lot of data in it. It's telling you the value of the function at all these points between 0 and 1, which means if you want to see what it looks like, you have to draw a graph. And that means that you can't visualize the whole vector space all at once. It's way too huge. But you can still visualize individual vectors. And the way that the vector space operations work in this space is the way that you have been dealing with those vector space operations for many years now. You add functions by just, I don't really know another way to say it. You just add them. You consider the value at each input x. You get the output values for that value of x for both functions, and then add the results. So for example, what would the sum of these two functions look like? So if this is f and this is g, what do you think f plus g is going to look like? Okay, that's pretty good. That's right. It's going to pick up the wave from this g function, but it's going to increase. That's not great. Something like that. All right, because that's how function addition works. You just, at each point, at each x, you ask, what's that? What's that? You add them together, and that gives you the sum. Okay? So this is the basic idea. Now, if I told you I was thinking of a function and I added it to g and then drew the resulting graph and it was exactly the same as g, right on top of it, what would that function that I added have to have been?
zero function.
The zero function. And what does the zero function look like if I graph it?
A line.
Yeah, just a line from 0, 0 to 1, 0. And what do I get out if I plug something into the zero function? 0. All right, I forgot who asked the question. Who asked the question? Yeah. So do you have a more specific question now? The main thing I heard was, what is the zero function in C01?
Yeah.
So I've answered that, but you might have had more.
So like, I forget like the exact problem, but it's on like one of the practice midterms, and it was like finding out if some restriction was a subspace of this. And
Okay.
you have to check like, is the zero vector in it? Like I wasn't sure how to check.
Okay. Okay, so I'll try to make up an example then. All right, that word is differentiable. I figured if I got the first 4 letters so you could read it. So I gave up after that. All right, so if we define some set S to be all the functions in C01 such that that function is differentiable and its derivative is equal to 0 for all x, is S a subspace? Would you say this counts as an example of the sort you have in mind? Okay. So the first question you want to ask when you're checking whether something is a subspace, well, actually, the 0th question you want to ask is, what does it mean to be a subspace? When you answer that question, you'll have a checklist, and then you can start working through them. So what does it mean to be a subspace? Contains a 0 vector. And closed under scalar multiplication, and closed under vector addition. So that's 3 things we have to check. So the first one is the zero vector of this vector space, which is to say the 0 function. Is it in this subset? So how do we check that? How do we check whether a function is in that subset? Yes?
You check if it's agrees with the definition.
Yeah, that's right. Because this set is defined to us with set builder notation, it's essentially giving us direct instructions for checking membership in the set. It says something is in the set S if it is differentiable and its derivative is 0 everywhere. So is that true of the 0 function? Take the function 0. Is it differentiable, first of all? Sure. And is its derivative equal to 0 everywhere? Yes. So this is fine. And then we want to check closure under vector addition. So we want to check that if you take 2 things that are in this purported subspace and add them, does it really stay inside that subspace? So f and g are in S, and we want to check that that implies that f plus g is in S. So what does it mean that f and g are in S? Okay, we don't have to go there. That's right, though. But just from the definition, what does it mean? It means the derivative is 0. So we're going to suppose that we have f and g in this set and write down what that means. Then is it the case that f plus g is necessarily in this set? Why? I didn't see who answered. Yes?
We have to prove that derivatives are also like.
No, you can use that.
Okay, the derivative of g is equal to the derivative of f plus g.
That's right. So it's a fact from calculus that if you have 2 differentiable functions and add them, the result is differentiable. Furthermore, the derivative is just the sum of the 2 derivatives. Okay, and then the last one, it almost always happens that these second and third conditions are virtually identical to check, so I'll just write it down for completeness. So f prime of x is 0 for all x. And that implies that c times f is also differentiable, and its derivative is c times f prime of x, which is c times 0, which is 0. Yes?
So on the second condition, you said that their derivatives are equal to 0, but how do we know that?
Because they're in the set, and the set is defined as the set of functions whose derivatives are 0 everywhere. So if I'm handing you two things in the set, what do you know about them? Their derivatives are 0. That's all you know.
But I'm confused why that proves that they're in the subspace if their derivatives are 0.
This implication arrow means that we get to assume what's on the left and try to prove what's on the right. So implication means if the thing on the left, then the thing on the right. So like if a prime number is bigger than 10, then it is odd. Right? You get to assume you've got a prime number bigger than 10 sitting in front of you, and then you want to show that it's odd. That's how if-then statements work. So we get to assume that f and g are in S to begin with. What does that mean? It means their derivatives are 0 everywhere. And we're trying to conclude that f plus g is in S. What does that mean? Its derivative is 0. And the derivative of a sum is 0 if the two summands have 0 derivative, because the derivative is a linear operation.
So for the f plus g function, all it takes for it to be within the subspace is that its derivative is 0.
Yeah, that's it. The definition of the subspace is all the functions whose derivative is 0 everywhere from 0 to 1.
Okay.
Yes?
So normally subspaces are defined relative to like a larger space.
Mm-hmm.
You'll say like
Mhm.
this is a subspace of all C01 or whatever.
Oh, yeah,
It
right.
never seems like that relative larger space matters when proving that something is a subspace. Does it ever matter? Would that ever affect our
No. No. Basically, the point of framing questions in this way is that, as I said earlier, I'm not asking you to learn all 10 things that make something a vector space. There's a bunch of boring stuff to check. But there are really 3 of them, or really just 2, closure under vector addition and scalar multiplication, that are typically the most interesting ones. So we nest these questions inside of a larger space where essentially you get to take for granted that someone's already checked all those boring conditions, and you can focus on the interesting ones. Yes?
Can you go over questions set after the It's a show that 2 is less than equal to the intersection. The dimension of the intersection
Oh, yeah.
is less than equal to
Do people actually want to see that one?
Did you say it would be relevant to the exam?
I didn't say that. I said if you are struggling, don't necessarily worry about it. I suspect that there are some people in the class who are sort of like really struggling to hang on, and they're going to feel demoralized if they try to do that question. So, I don't know, why is that so striking? Yes.
Can we go over number 2 on the last homework?
Yes, but first I want to ascertain whether you want to see this
Oh,
U intersect V thing.
Sure, why not?
Okay. I don't think it's going to take that long. Okay, so the setting in this question is that we have 2 subspaces, U and V, of some bigger subspace W, and the dimensions of the 2 smaller subspaces are 8 and 4, and the dimension of the bigger subspace that they live in is 10. And we want to show that the intersection of the 2 subspaces has dimension at least 2. So first of all, where do you think the number 2 is going to come from with those 3 numbers? No? Yeah. 8 plus 4 minus 10 is where it's going to come from. So basically the idea is if you have a 10-dimensional if you have a 10-dimensional vector space, you can fit in two vector spaces of dimension, let's say 6 and 4, that only intersect one another at the 0 vector. Because you can just take a basis and just split it up into two, push 6 to one side and 4 to the other side, and consider the span of the 6 on one hand and the span of the 4 on the other hand. And they intersect only at the 0 vector. But if you have 8 instead of 6, then there are two extra sort of directions that you can't squeeze in somehow. So you end up with this excess of 2. So that's what's going to happen. But figuring out how to go about it takes a little thinking. So first of all, rather than pulling you through it, I think maybe I should just present the ideas, and then you can stop me if you have questions, because I don't want it to take forever. I don't remember what letters I used. When I wrote up the solutions. But anyway, you want to understand the relationship between several vector spaces. There's U intersect V, there's U and V and W. That's 4 vector spaces going on at one time. And the way to capture the idea of different sort of directions within a vector space is to relate bases of these different spaces. But you can't start at the biggest vector space and go down, because you might not, if you start with a basis of the biggest vector space, it might not actually contain bases of your smaller vector space within it. But you can go the other way. So let's start with a basis of the smallest one, which is U intersect V. And this K here is whatever the dimension of U intersect V happens to be. We're going to figure that out later. But U intersect V is an intersection of two subspaces. That means it's a subspace, so it has some dimension, and we'll call it K. Then let's conjure a basis of this vector space, U intersect V. And then what are we going to do to come up with more bases? Yes.
Why would you want to increase the bases?
It's nice to have a single basis of the bigger space. Well, ideally W. Maybe we can't get there, but it would be nice to have a basis of U at least that has the first few vectors being a basis of U intersect V. Because then we can understand the relationship between U intersect V and U. Because we've got access to two bases of the two spaces that are related to each other, in the sense that one is just the first few vectors of the other one. Yes? That's right. Yeah. That's a sort of bare hands way of doing what I want to say, which is just extend this basis to a basis of U. And the way you would do that algorithmically is you would just grab something that's not in the span of U intersect V and add it on. And then grab something that's not in the span of that and add it on until you have 8 total vectors. That would give you a basis of U. But we learned in class that you can always extend a linearly independent set to a basis. This W1 up to WK is linearly independent because it is already a basis of this smaller space. So we can extend it. And how many vectors is this basis of U going to have in it?
8.
It's going to have 8 because U is an 8-dimensional space. So the first, however many, we're not sure how many yet, but the first sum amount came from U intersect V, and then the rest of them come from U. Okay, and then we also want to extend it to a basis of V, similarly, because U and V are symmetric in this problem. Well, almost. They have different dimension, but whatever. And now I have to make up some slightly different notation because we've already used W1 up to W8. And there are only going to be 4 things here. So I sort of arbitrarily, when I wrote up this solution, decided to call them VK plus 1 up to V4. So that's maybe a little weird. I don't know. It's however you want to do it. Point is, we take some vectors that are sort of our core. They're a basis for our intersection of these two spaces. And then we just fill them out to grab the whole space U, and then fill them out on the other hand to grab the whole space V. Yes?
If we were doing this problem on the midterm and we didn't switch to V, we just kept it as W up to W4, would that be marked as incorrect?
Maybe not if it was really clear what you meant, but it's not good math to use the exact same symbol for 2 different things. You would probably confuse yourself. You could call these like V1 up to whatever the right index would be. I didn't do it that way precisely because I didn't want to figure out that index. Yes?
Is it possible to do a proof by contradiction?
I think so. Like assume that it's 1 or 0 and then come up with a contradiction.
Because like for example, if you show that they're all unique, if like dimension, if U and V do not overlap at all, then they span like they'll span like a vector space with dimension 12. Okay, could that like start a contradiction?
So that works to show that the dimension of U intersect V is at least 1. You can say, well, if it were 0 and they just intersected at the 0 vector, blah blah blah, make some argument, that would be, you could get a contradiction. But then how would you rule out that the dimension is equal to 1? Feels like you'd have to do it again, which you could do definitely. But the ruling out 1 is trickier than ruling out 0. So we're just doing them both at the same time. Yes?
How do you know that WK, or that you know K is not equal to 4? So if it is equal to 4, then there are no extra vectors.
Yeah, there might not be in this list might have length 0.
Right.
If K is 4, then this list would not have any vectors in it. That's
So how do you need to account for that if you're writing proofs?
no. It's totally fine if you write, people in math often write things like 1, 2, 3, ... up to n. Right? That's a very understandable piece of notation. Just means the first n positive integers. What is that if n equals 1? Well, it's just 1. So the writing of the 2 and 3 was wrong in that case in some sense, but that's fine. People know what you mean.
Okay.
You can leave these sort of degenerate cases as sort of unspecified. That's a good question. All right, might be none, but it doesn't really need to be mentioned. Okay, so now we have these 2 different lists, and what are we going to do with the lists? What feels like should be done? We have one list of 8 things, one list of 4 things. We should put them together and see what happens. Okay. So then this list has 12 minus k vectors in it now. Because it has 8 w's, and then there are 4 minus k vectors left, the v's at the end. Right, like if k is 2, then it would be, you would just have v3 and v4. Right, if k were 1, you'd have v2, v3, v4. So you just feel it out. There's 4 minus k v's. So altogether, there's 12 minus k vectors. And then we're going to claim that this list is also linearly independent. And this really explains, I think, the answer to the question that we had earlier, which is why do you start with a smaller space, come up with a basis, and then fill it out to a basis of these larger spaces? This is why. When you do that, you guarantee linear independence when you start putting these spaces together. And that's helpful. So how are we going to show that? Well, what are the 2 ways we have of showing that a list of vectors is linearly independent? Yes?
I just have a question on the linear
Okay.
independence.
Yeah?
Which is just, how can you, like, I understand why each individual list is linearly independent, but when you, like, put them together, couldn't, like, vk plus 1 be w5 or something?
Yeah, that's what we got to worry about. That's what's coming next. That's definitely correct. You take 2 linearly independent lists and you mash them together. Who knows what's going to happen? But in this case, we'll see that it's still linearly independent because of the way that we constructed them. So what are the 2 ways we have of showing that a list of vectors is linearly independent? You definitely want to have these on lockdown. Yes?
My solution set the solution.
Okay. Yeah, so that works in Rn, but what about in abstract vector spaces? There's the linear dependence lemma, and there's also the definition. So the only way to achieve 0 as a linear combination of these vectors is to have all weights be 0. That's the definition. And then there's the linear dependence lemma, which says that a list is linearly independent if it is the case that every vector in the list fails to be in the span of the vectors that precede it. So that one is easier to deal with here because it gets us immediately up through the first 8. So how do we know that none of those first 8 vectors are in the span of the vectors that came before them in the list? Yeah, it's a basis. W1 up to W8 is a basis of U. So it's already linearly independent. So no work, very easy. So the first time we have to start thinking is when we hit V k plus 1, this one. So you might have to worry that Vk plus 1 is in the span of W1 up to W8. Yes?
Did you move all of the vectors that are in the intersections though? That's like 12 minus k vectors.
This includes the first KWs are in the intersection. And I included them. So I'm starting at W1 here. The reason there's some missing is that when I go to fill out the basis of V, I don't necessarily get 4 V vectors, right? Some of them are accounted for because they're in the intersection. So W1 up to W8 is already linearly independent. I guess I'm going to have to flip back here because there's so much relevant information on that other page. Now, how can we be sure that Vk plus 1 is not in the span of these 8 vectors that came before it in the list? This is the trickiest part of the proof. Yes.
Well, you know that it's not at least in the span of W1 to WK because of the way that you defined it, but I'm not sure how you get from WK plus 1 to W8.
Okay, that's good thinking. So we know that it's not in the span of W1 to WK because those vectors are in this list. So if it were in the span of the first KWs, we would have already had a problem when we cooked up this basis of V. Oops, I didn't write that. Sorry. That was a basis of V. Okay, so but how do we know that it's not in the span of all 8 W's? Yes.
Because it's it's not in the intersection of U and D because you have to expand the intersection to get those vectors. And so because it's not in the intersection of U and D, the bases W1 to W8 won't. They won't be in the span of W1 to W8.
Yeah, that's right. So the point is that W1 through W8, all those vectors are in U. So if VK plus 1 were in the span of those first 8 vectors, it would be in U. And we already know it's in V because it's one of the basis vectors of V. So if it's in U and V, then it's in the intersection of the two. And that would mean that it's in the span of the first K ones, W1 up to WK. So VK plus 1 is not in the span of W1 up to W8 because VK plus 1 is in V for sure. It's a basis vector. In that basis we had a V. And if it were in the span of W1 up to W8, then it would be in U as well. And since we already know it's in V, it would also be in U intersect V. Well, we know that's not possible because of how we came up with VK plus 1. We started with the basis of U intersect V and extended it, only grabbing things that were outside of U intersect V to fill out, to get a basis of V. Okay, and then the same idea is going to work as you continue to go on. The rest of the V's aren't in the span of the stuff that came before for the same reason. Yes?
Why would VK plus 1 or plus 2 not be, like, for example, in the span of like the previous vectors? Like, what if VK plus 2 is in VK plus 1?
Okay, that's a good point. Yes, you're right. The other V's are slightly more complicated than the first V because you have to worry about that first V getting in the way somehow. But it's not a big deal because if there were some, so if let's say V4 were in the span of all the ones that came before, then you could just subtract off whatever linear combination of the other V's that show up in the linear dependence relation. You could subtract all that stuff off and get something that's in the span of these last few V's. And That would be in the span of the W's. I wouldn't worry too much about that. Yes?
Can you say again how we know that VK plus 1 isn't in the intersection of U and V?
Because VK plus 1 showed up here in this basis after the vectors that formed the a basis for U intersect V. So once we get up to WK, we've already covered all of the U intersect V space. And then we're adding other stuff besides that. So anything that appears later in that list cannot be in the span of the stuff that came before it. Yes?
In other words, by the linear dependence lemma, that's how we know that's not the span of one's previous.
You don't need the lemma, actually. You just know that if this is... You can think of it that way if you want to, but as soon as you know that this is a basis, you already know that VK plus 1 is not in the span of the W's, W1 up to WK. Because if it were, that would be a linear dependence relation, and that would break linear independence. The strength of the linear dependence lemma is in the other direction, to show something is linearly independent. Because it says that you can check these conditions one at a time. Look at this vector, see if it's in the span of the ones before. Okay, look at the next vector, see if it's in the span of the ones before. If the answer is ever yes, then automatically the list is linearly dependent. But if the answer is no all the way to the end, then the linear dependence lemma comes along and tells you you're done. You know that this list is linearly independent. Okay, so anyway, the point is we have this list of 12 minus k vectors, which is linearly independent. And how does that conclude the proof? Yes.
We know that U is 10, and if it's going to span 10, then it has to be x 10 vectors, so k must be x2.
That's right. Well, almost. So we don't know that this list actually spans
But we know
W.
It has to be in W.
But we know that it's in W and it's linearly independent. So, and we have this result. So remember, we learned that the length of any linearly independent list is less than or equal to the dimension of the space, which in this case is W, which is less than or equal to the length of any spanning list. All right, that was a thing we leaned on pretty heavy. All right, we're just using this first part of it here. We have a linearly independent list of length 12 minus k, and we know the dimension. And that implies that k is at least 2. The picture here is that you have, we can make a fanciful Venn diagram. You have some space U and some space V, and then they intersect here. And if you come up with some vectors that are a basis of this intersection, and then you fill out that basis to get a basis of U, and separately fill it out to get a basis of V, then all these vectors you get when you put all that stuff together has to be linearly independent. The fact that within each piece you assure that the vectors are linearly independent, and then they're sort of reaching out into separate spaces that don't intersect, or separate parts of the vector space that don't intersect, it means in the end you're not going to get any linear dependence relations. So like in this picture, this is like W1 up to W8, and then this is the first few W's, and then the V. So those are W1 up to WK. That's, I guess, V4. And then these ones are the rest of the W's up to W8. Okay, this question is a little much for me to ask you to put together on an exam, but it has a lot of good stuff in it. So I think it's a helpful thing to think through. All right, sort of like in baseball, you know, they have these weights that they put on the bats so you swing just before you go to the plate to sort of like train your muscles to be used to a very heavy bat. And then when you actually have to swing, it feels lighter. You can swing the bat faster or whatever. So that's a little bit what I'm going for here. Also, I slightly overshot the difficulty that I was intending. Yes?
So what would be a level that would be more appropriate?
Slightly less stuff going on. I mean, the tricky thing about this one is that there are so many pieces. It starts with kind of a tricky idea, and then there's a lot of stuff for you to check. So I could easily ask any one of these components. I mean, no one thing in here except maybe the very beginning is all that hard, but there's just sort of too much to ask you to check at once. But I could like extract certain pieces here and simplify it and make a question. Yeah, I could potentially ask a more scaffolded version of this sort of thing. Probably won't do that though. Yes?
I see where the fact that like the linear independent list is smaller than the spanning list comes from, but where does the part about the linear independent list being smaller than the dimension?
Well, the dimension is the length of any basis, and a basis is a linearly independent spanning list.
Okay.
So any spanning list gives you an upper bound. Yeah, okay. Maybe I should explain that.
But isn't that like contradicted by the basis of the kind of definition?
Not quite, because you have to be concerned that there's some sort of tricky combination of the V's and the W's that would get you the next V. But VK plus 2 is not in the span of these ones, because if it were, then it would have to be, there would certainly have to be some all right, so like if VK plus 2 were in the span of the ones that came before it, then that would mean that it's equal to some linear combination of those ones. And then you could just take this term and move it over. Maybe I'll do that in a separate step. And you would have this thing being in the span of the W's. And this thing is NV, but not U. Because if it were in U, then we would already, if it were in both of them, then we would already have had a linear dependence relation in the original basis of V. So it's basically the same argument. After you subtract one term, you move one term over, it's the same thing. All right, it looks like maybe the questions are petering out, and in any case, that is enough for that question. What was the other one? Someone asked about a different one.
I mean, I asked on problem 2.
Okay, what did that say?
It was like subspaces, the inverse transformation, how do you prove that it's in subspace? I'll tell you the example.
Oh, right. So if you have,
suppose that T is a linear transformation from V to W, and that Z is a subspace of W. Show that T inverse of Z, the set of vectors in V that maps to some vector in Z, is a linear subspace. I can go again. Of the linear subspace.
yeah, so this is one of the ones, this is a type of problem like the one that I wrote to you about at some point last week, which is pure definition chasing the whole way through. So there are a lot of pieces to chase down, but none of them None of them push very hard. You just ask the question that the definition forces you to ask, and it has some immediate answer.
So like, does it have 0, I guess?
So we want to check whether something is a subspace of some vector space. So the first thing we need to ask is the 0 vector of the larger space, is it actually in T inverse of Z? And what does that mean? What does it mean for one element to be in the pre-image of a particular set under a given function?